in the Arctic. Or the Antarctic.
Yeah.
Yes, did you, Steve?
Steve's recording. Okay.
Yeah.
Yeah, I was telling him about
Yeah, we talked with Steve.
I see you've got an illicit grant.
Yes.
Congratulations.
Thank you.
We need to go over this one just now.
Yes,
We
yes,
did
yes.
That's nice. Yeah, oh, okay. I saw the internet. Grant.
from geoscience, which is kind of a
It's
format.
promotion science.
Ocean
Yeah,
science.
yeah, the density things. I mean, it's pretty much what we proposed for the
But
oil spill
there's one
problem.
thing probably
They
is
didn't
kind
give
of
it, but
related
then
to you guys is that
it's the cloud exchange. You have two different densities. It forms a density
the
wave.
gradient
So we have
is some, people mentioned that it has to be precise, it has to be accountable. So now I already revised this kind of policy here. So we only have two parts. One is attendance, another one is reports. Here I want to mention that the reports only for the any research center basically is outside the speakers. So other presentations are more kind of related to professional development. So it's kind of for the graduate students, specifically designed for the graduate students. So now that's where you have to write a report. So basically it's kind of give you some kind of information. And then the attendance is a 50%, and then if you it's not covered for early leave and in the late departments. So that means that every time you feel late or you feel early, and then you have deduction for the point. So why we do that is because we're trying to make it very consistent. So although this is a PhD program, okay, I don't want to keep up so much time on presentation.
Do you want to go ahead? No. Can I go ahead? Okay. I'll do it. Okay, good morning, everyone. Thank you very much for inviting me to the Department of Mechanical Engineering and also Geological Sciences. I met some of the professors there. Just I want to give the little introduction about our program and what we do in our laboratory. So I'm Subra Bulusu. If you don't know the first name, so just short name is Subra. So I'm heading the Satellite Oceanography Laboratory, which is connected with the Department of Earth and Ocean Sciences. So we have the School of Earth, Ocean, and Environment and Sustainability. The school is there. Under the school, we have Marine Science Program and the Department of Earth and Ocean Sciences, and we have the Environment and Sustainability. So in our lab, we don't do just only the satellite oceanography, but also we do the ocean modeling. So I will show you some of the things what we are doing recently. So this is not just my work, also my collaborative with my students too. So today I want to show you, the recent work, what we are doing. So everyone is interested on that, and a lot of funding is coming from NASA about the salinity. We use the salt every day on our dining table, but the salt in the ocean is very important for the, for the ocean circulation and also for hydrological cycle. So what is the salt? So the saltiness of the seawater. So really we measure the saltiness of the seawater, like for example, if you have the 35 grams of salt dissolved in 1 kilogram of seawater, then we say 35 parts per mille or 35 PSU. Or sometimes we also use parts per thousand. So the units varies, differently, because a lot of people are using either PSU or PPT, or sometimes some people says there are no units for salinity, because in reality we are not using, nowadays we are not measuring the salt, how much in the water, and we are doing from conductivity, right? From the conductivity, you are getting the salinity. So some people argue that there are no salinity units. But I would prefer to use PSU, practical salinity units. So if you look at the, in the fresh water, the salinity are less than 0.5. But if you go to the H-rain waters where the river water mixes with the ocean, there you see the drastically the salinity changes from 0.5 to 30 PSU. And if you go to the ocean, salinities are like above 30 PSU. If you take the global salinity 32 to 37 PSU, you will see. So another thing, if you can stop me if you don't understand anything anytime. So this is not the salinity, but what I'm showing is the sea surface temperature. So the sea surface temperature from satellites are available from 1975. But the technology was not there to measure the salinity until last 2 years. Why it took a long time, right? But if you look at the temperature map like this one, it's very rich information. What is, we get every day, from satellites, like this, images, and you can do a lot of things, you can understand a lot of dynamics in the oceans. For example, you can see the tropical regions have very, high sea surface temperature, and quickly you can see here the, in Atlantic, the, Gulf Stream, and also in the Croatia region, you can see the, Pacific, you can see the Croatia current, so like that you can see, very quickly, with the satellite map. And also in the Southern Ocean region, you can see the Antarctic circumpolar current, the front you can see here with the cold waters. So you can get this kind of information in one snapshot from the satellite data. But we don't have this kind of information from satellites on salinity. So, but we have now. So this is the global salinity map. The schematic. Like last 40 years or 50 years back, we don't have a lot of observations. So people know, the Atlantic is much saltier, than Pacific or Indian Ocean, except in Indian Ocean is Arabian Sea or Red Sea area, you have the high salinity values. So this is the schematically we know. But in 1990 to 1998, we have the WOS, that is called World Ocean Circulation Experiment. So that time, a lot of countries participated to measure the temperature and salinity. So we got the global salinity values, most of the oceans. So now we know that, the values like 37, like that in Atlantic, and also Mediterranean is high salinity waters are here, and the Pacific we have here and here, the subtropical regions, and of course Arabian Sea in the Indian Ocean we have, high salinity waters are there. So we know from the observational point of view, so what kind of salinities we have. But this is, climatology, last 10 years of data, collected, that's what you're selling. But you need to know what is happening, day to day, or at least 10 day, or like that. So we need to have the satellites. And for example, for curiosity, if you want to know why the Atlantic is saltier than the Pacific, the simple reason is, it highly evaporates here, so the evaporation is much higher in Atlantic, and it evaporates here and dumps that water in the Pacific. So the Pacific is becoming less saltier or fresher than the Atlantic. If you look at the Atlantic and Pacific, the only place it is connected between these two, or this is called Drake Passage. This is the Drake Passage where the the Pacific waters can enter into Atlantic, and Atlantic waters can enter into the Pacific Ocean. Otherwise, there is no any connection between these two. So Drake Passage plays a major role in the global ocean circulation. We will talk about in a few minutes on those too. if you go to the global surface density, if you know the temperature and if you know the salinity, you can calculate the density. So right now because of the satellite data, both the temperature and salinity is available. You can calculate these kind of maps to get the density. So why the density is important? So density is the one drives the ocean currents, right? So the waters are moving from one basin to other basin, because of the density. If you don't know the density, then suppose what happens if waters are stable, waters are not moving from one basin to other basin, then the Europe will be very, very cold, right? Because the warm waters from the Gulf Stream are going to the Europe, right? So if the warm waters are not moving from Gulf Stream to the Europe, then Europe will be much colder than what we have right now, right? So it's very important for the ocean waters. The density is very important. And the density-driven currents are also very important. So if you look at the, in the past, we don't have a lot of salinity observations. So we used to, with the hydrographic observations, we know that the salinity varies from 32 to 38 like this. But if you have the evaporation and precipitation, if you plot like that, then you can see the similar kind of pattern you are seeing in the salinity also, like evaporation and precipitation, right? Only thing you are missing is the magnitude. So the magnitude is much different. You are not seeing this much of magnitude here, right? So what you are missing is here, if you add the rivers, right, river runoff, and add the melting of the ice from the polar regions, if you add those two, then you are close to the salinity, right? But getting the right accurate river runoff or river input is very, very hard because there are not a lot of observations at the rivers, right? So that's, and the melting of the ice nowadays you can get from satellites. So if you do that, if you add that one to this, then you will end up in the salinity, right? So that is a very crude way to get the salinity information from E minus P. So last 10 years, I am one of the PIs on the Aquarius salinity mission, which NASA was launched. So we are interested not just knowing the salinity, also how we can use the salinity for climate prediction or El Nino, or for the hurricane prediction, or the global water cycle, to understand those things. So we were working hard on that last 10 years. So finally we are successful on that salinity measurements. So I will show you there are two satellites. One is the soil moisture and ocean salinity. This was launched by the Europeans. Actually, our NASA Aquarius salinity mission supposed to go before them, but we were collaborating with Argentina. Argentina was in a bad economic situation last 5 years back. So our satellite was delayed, and the Europeans, they claimed they launched the first salinity mission now, right? But I will show the problems with the soil moisture and ocean salinity mass. This is a wonderful mission. When it is on the land, you get the soil moisture. When it is on the ocean, we get the salinity, right? So you are getting two parameters same time from this satellite. So the goal was to get the large scale, to understand the large scale, circulation or water cycle or the climate system. As I mentioned before, a lot of objectives like understanding the climate, also we can use, this satellite mission. Before the satellite was launched, we have several meetings on that. So for example, one Global Ocean Data Assimilation Experiment, that group, they want 0.1 PSU accuracy, 200 kilometer resolution, and 10 days. And another group asked like this. So finally, the ESA went up and said, well, we will do 0.1 and 200 kilometers, and not 10 days, we can go do the 30 days. Right. So this is what you are getting right now. Every 30 days, in 30 days, you will get the 200 kilometer resolution and 0.1 PSU. But we didn't reach to 0.1 PSU. I will show why we are failed to get not getting that good accuracy. Okay, so it was launched in November 2009, so it's almost now 3.5 years of data we have, and soil moisture and ocean salinity we are getting, when resolution is 1 to 3 days and 45 kilometers, and accuracy is supposed to be 0.1, but we are at 1 PSU right now. So to get from 1 PSU to, I would say in the open oceans, we are at 0.5 PSU, not 1.1 PSU. So it takes, for a while to get that kind of accuracy. So the technical concept is very simple. A lot of people, like radio astronomy people, used this kind of technique on the land to, for radio astronomy. But putting that technique on the space, it took a lot of time. So what is the technique is, if you look at the antennas, there are 3 antennas connected together. So the receivers are there here. The total receivers are like 52 receivers. So you can see the receivers are like this, right? So this is the L-band passive microwave radiometer, and 1.4 gigahertz. And so the spatial resolution is 20 to 50 kilometers, and revisit time is 1 to 3 days, and mission duration is 3 to 5 years. So still, it is working. So when the satellite is stub mode, it looks like this, and the racket looks like this one. All those things. I not want to go much on that, but this is what you need to know. So when the satellite is moving, pass, ascending or descending pass, you are getting the data, like this one. So what it's showing is, because you have the 52 receivers on the 3 antennas, so each receiver gives like a hexagon like this one. So the hexagons will give that. So you are covering the data at one point. So it is called swath. So what it is seeing is, 2.4, every 2.4 seconds, you are getting the 1,000 by 1,000 kilometers of data. So if you take the swath of this data, is 1,000 by 1,000 kilometers. And the spatial resolution is 43 kilometers and 3 revisit time. So if you're looking 1 point here, after 3 days, it is coming back to the same point, right? So it takes like a 3-day repetition. So suppose, think about that, if you are moving your lawn, right? So then you are taking your lawn mower, like this. So the satellite is also doing the same thing, but what kind of swath you are getting is almost 1,000 kilometers swath is you are getting here. So don't think that the satellite is giving the salinity at one point. It is giving the whole swath, right? So you're getting a very high resolution in space from this satellite. But always, like any satellite, you need to do a lot of corrections. So because the satellite, the radiation is coming through the ionosphere and atmosphere, and also once it reaches the the ocean surface, you need to do the corrections for roughness correction and wind corrections and all those things. So there are error sources also there. So the main thing you need to know, so really how the satellite is measuring salinity, right? So that is very important. So what the satellite is measuring is the brightness temperature, right? So from brightness temperature, you can calculate the dielectric constant. From dielectric constant, you can get the salinity, right? That's what even the chemistry people does the same thing, right? The chemistry people does get the dielectric constant. From dielectric constant, they get the salinity. Same thing we are doing, but one more step we have in the satellite technology is from brightness temperature to dielectric constant. That's another thing we are doing. So here you can see here the brightness temperature the satellite measures, which is a function of frequency, angle, temperature, and once you have that, then you can get the dielectric constant. Then we do the roughness corrections and all those things. Like this, for example, we take the salinity and the brightness temperature, and we see, what kind of, sea surface temperature. Because from brightness temperature, you need to get the, sea surface temperature. So that is very important. So we do that. Then we will get the dielectric constant. So this is the way we do. Salinity measures the satellite measures the brightness temperature temperature. So the brightness temperature is function of E and T. So, so E is water emissivity and the T is the temperature. So once you have the TB, then you can get the dielectric constant. If you put in this equation, then you are getting the salinity, right? So, the technology, it's not, by telling, with the 4 equations, it's very simple, but doing is a little bit complicated because you need to do a lot of, corrections and all those things. So these are the things what we do every day in our lab. We get the satellite data every day, and then we do corrections for roughness. What kind of roughness corrections? So we plot and we see the correction, and also we see for the other drag coefficient corrections and all those things. So we apply so many things, and finally we bring to the salinity product like that. So the main problem what we are facing right now is the radio frequency interference. So what is the radio frequency interference? What you are using your cell phones, right? So your cell phones are causing the problems not in US but in the Asian countries, because they are using the same frequency what the satellite is using, right? So in Europe, after this satellite was launched, they banned all the cell phones not to use 1.4 gigahertz. But they can't come to India or China or somewhere and say you can't use this one. Who are you to ban, right? So that's the problem. So we are having, so you think that, oh, we are using on the land, how it causes a problem on the ocean side. But suppose take in India, India continent is coming all the way to here. So that is causing problem. All the North Indian Ocean, the data is contaminated with the radio frequency interference. So we need to remove that kind of data. So when we are processing, we are not getting the data in the North Indian Ocean at all. And the same thing along the coastal regions. All these coastal regions are contaminated by radio frequency interference. So that is a major problem with this satellite right now. So that's why we are not getting good accuracy. Also, in the other places, I will show you in a few minutes. The SMOS is the first mission. So Europeans got that. They launched the first satellite mission, salinity mission. So the new concept and still, challenge, because there is no way you can validate, because we don't have the lot of satellite data before. So the calibration and the validation is still working. So on the other hand, the NASA has launched another satellite called Aquarius SAC-D. So this is the collaboration between the NASA and CONE, which is Argentina space agency. So this one is the collaboration between Argentina and the United States. So the SAC-D, the Aquarius is it gives only salinity. It don't give soil moisture. So it don't work on the land. So when it is working on the oceans, it gives the ocean salinity. And also the advantage on this satellite is we have the scatterometer on board, so we can get the correction for the roughness correction and winds and all these things we can do on board, these corrections. But the SMOS, the Europeans doesn't have the scatterometer on board, so they can't do any onboard corrections. And the resolution is 7 days and 150 kilometers, and the accuracy is 0.2. I'm very happy to say we already reached to 0.2 in some places, and only the coastal regions we are not reached that 0.2, but already we reached to 0.2 in 30 days repetition and 150 kilometers. The only thing, the swath is not 1,000 kilometers like SMOS, and this swath is only 400 kilometers. I will show you in a few minutes.
What do you mean 30 days?
So we take the average of 3-day data and make it to 30 days, because 3-day you are not covering the whole globe, right? So this is the monthly product rather than the 3-day product. Okay. So how it works? Okay. So the Aquarius has the 3 antennas like this one. So if you take I would say the footprints, if you combine all these footprints, you are coming to 390 kilometers, right? 390 is almost 400 kilometers you are getting. Whereas you have seen the SMOS has the swath, right? That is 1,000 kilometers. So that is the only disadvantage with Aquarius. But you are getting the accurate data every 7 days, and so approximately you are getting 4 repeat cycles. So you can get the weekly data from the this satellite, and when it is flying, then you can see the antennas are looking at different angles like this one, and so we get the data like that. So what the advantage of this satellite? So this advantage is right now we have these sparse oceanographic observations with this satellite. We are hoping like this with 150 spatial resolution and 0.2 PSU monthly accuracy, and right now it is a 3-year mission, but we are hoping it will go beyond that. So by 3 antennas, blue, green, red, it is covering. This is one single day. In a single day, you get the data like this. So in our lab, every day we get the data for all these antenna data. We get like this, and we process, and we have the data like this one. So for example, if you're working on the Indian Ocean, then you have a couple of passes are there, right? So 1, 2, 3, 4, so almost you're getting 5 or 6 passes you're getting every day. So the same thing, and so this is the real salinity data. So once the data comes, we process it, and you can see the salinity 30 to 40 PSU. We are putting the range. Then you can see the salinity how it is changing. The high salinities are in Atlantic. You can see quickly within the daily data. So, but if you want to see the global maps, I would say you should use the weekly data, not daily, right? Because still you have a lot of gaps are there in the daily data set like that. But if you go to the polar regions, so in Arctic, you are getting very high resolution data because it's, you are not missing any data all the way to Arctic. You can go, but whereas if you go to Antarctica, you are missing, because of the, the passes are merging, so you are missing a lot of data in Antarctica. Of course, it's all ice, so you don't need to worry, right? But you're getting a lot of data, there in Antarctica too. So this is what in our lab you see in our screens every day. When we are processing how the polar regions are doing, and how the oceans are doing, and the global domain, we will put like this. This kind of data sets you will get for daily, if you're asking from us. So once you have the data, then we do validate. So in the for example, in the Pacific Ocean, you can see, the salinities are very high. Salinities are here, and so this is the model. We have the HICOM model, or OGCM here. I'm showing 1/8 degree different model, and Aquarius is doing here. And if you take the World Ocean Atlas, observations, looks like this one. So if you compare these two, you are seeing a lot of mesoscale structure than the observations, right? So, that is so you can do a lot of things using the Aquarius data. And also, if you do the smoothing, then you are getting very close to the model simulations like this one. So normally we take the observations to compare the models, but in our case, this is the first satellite, so you need to compare with the models. That's the only we have right now. So, and on the other hand, you can also compare with the random buoys are there. I will go in a few minutes, how these work and all those things. And if I compare with that, also it is doing pretty good. So the summary of this one is, very quickly, I want to show the SMOS accuracy is, I would say, 0.5 to 1.5. That is the accuracy we are getting right now, and 3-day and 45 kilometer resolution. Whereas Aquarius, we already reached it to 0.2. I would say 0.2 to 0.3, in the worst case. But there's a 7-day resolution and 150 kilometer resolution. So this is the product I would suggest, if you're using for your studies, to use the Aquarius data. Okay, so some of the things before I do the validation of this data, I want to show the this is the model we use, the global HICOM, which is the hybrid coordinate ocean model, which is the Navi model. So we use this model to validate our satellite data. I don't want to go beyond all these things, but what I want to show quickly is this is the hybrid coordinates. It goes all the way to the bottom, and it has the mixed layer options. You can choose which mixed layer you want, also KPP, GAS, and all those things if you know some fluid mechanics. And so if you go to deeper layers, because it is a hybrid coordinate, terrain flowing, you can see along the coastal regions, you can see the terrain flowing also like that. And so this is the example. If you are using the level model, looks like this one, and sigma and g looks like this, and sigma coordinate only just density coordinates looks like this one, and hybrid coordinate looks like this one. So you have the different structure along the coastal region. So the next slide I will show you, you see the difference of the salinity. Can you see now? If you're running the level model, you are getting the like this. But when it comes to the hybrid, then you can see along the terrain flowing. Can you see the difference? So this is representing the more accurate ocean than running the ocean model with these three different formats, right? You agree with me? So I would say the hybrid coordinate ocean models are best for for the oceanography. And also the floats I showed you, the black dots before, these are called Argo floats. So the Argo floats, there are so many floats in the ocean deployed by the different countries. So the Argo floats looks like this one, and so once you deploy it from the ship, they go down to almost to 2,000 meters depth, and after 10 days, they come back here. So every 10 days they come to the to the surface, and so you can collect the data from the satellites, and the satellites will telemetry to the different data centers. So when it is the ocean, looks like this one, and so we have so many floats out there. So if you can look here, almost 4,000 floats are there, deployed by different countries. All the countries participated in this, and you have. Even though you have seeing like this one, suppose, for example, I'm working on the Indian Ocean, then you can see here, so many floats are there, but those are only 700 floats, okay? And they touch the, these continents, and they don't work, and sometimes they die in the middle of the ocean. So, so still you have the big gaps. If you go to the Southern Ocean, you don't have a lot of floats here. So still, that's why we need a satellite, which gives the global ocean data set like that. So suppose if you take 2006 and 2005, 2006 Argo, all the floats 1 year, then you get the data like this one. So you are missing a lot of information in Atlantic and some other places, right? So, but if I smooth it, then it looks like this one, which is close to the model or to the satellite data. Okay, so this is what you are getting from the Aquarius, the average, August 2011 to April 2012 looks like this one, so you can see the high salinities are here in the Atlantic and the Pacific, and also Arabian Sea like that, right? So that's what we have right now. So I will show you some of the applications. Why we need the salinity? Why we spend billions of dollars? That is your money, right? Your taxpayer money, right? So why we spend and we wasted that money? No, we are not wasting that money. So you can see here. So if you look at the E minus P and salinity, looks very close. So right now the E minus P looks top panel looks like this one, and the salinity. What we are missing is only the river runoff and the the melting of the ice. If I add to this, then I will be close to this one. So then I can tell the hydrological cycle and all those things. So one of my student, PhD student, he is working on, what he is seeing is the places which are, saltier, salt is here in Atlantic are becoming saltier and saltier because of the global warming, right? And also the places where it is freshening or the less, salinity, they are becoming freshening and freshening, right? Even last 10 years, we are seeing, these places are freshening and freshening. That causes the hydrological balance or the cycle is changing, right? So that causes the problems on the land too, right? In 50 to 100 years, think about that. We might not have a lot of fresh water, drinking water, right? So ultimately, it's economic consequences on the land also, on the whatever happening on the ocean. So we need to be very careful, on those things. So still, we want to quantify it, how much it is freshening and how much it is saltier, becoming saltier, right? So that's very important for hydrological cycle. So if you look at the Aquarius satellite and SMOS and Argo observations and the HICOM model, everything looks similar with your eye, right? But if you take the differences, you see the differences are, still there are a lot of difference between 1 to 1 PSU. So 1 to 1 PS is a lot of change in the hydrological cycle. So, for example, like Amazon plumes, the Amazon plume is here. So you can see here we have 1 PSU difference between the SMOS and HICOM. So SMOS is showing higher than reality or in the model, right? So the same thing here, and the Argo is observations, Aquarius is observations, and the HICOM is model simulations, also showing a lot of difference here. So we are finding out whether the satellite is doing, where it is working and where it is not working. And also you can see here the standard deviation, a lot of differences in the intertropical Pacific zones, so you are seeing the differences are here. And also in the Pacific, you have a lot of differences there in the standard deviation. So what is causing those differences? So still we are, working on those things. And if you look at the Atlantic and Atlantic, North Atlantic and South Atlantic, and the Pacific, and also Indian Ocean and world oceans, you can see the salinity changes from 2010 to 2013, right? So suppose if I plot this one from 1950 to now, then you can see, the places are becoming saltier and saltier some places and fresher some places, right? So we are looking those things, those causes and all. I will go very quickly. What I want to show here is Atlantic Ocean, North Atlantic and South Atlantic. If you do the scatter diagram between the Aquarius and SMOS at the whole Atlantic basin, then you are getting very good correlations, right? 0.8 is pretty good. If you're taking the whole basin, the satellites are doing pretty good. But if you go to the small regions, then either SMOS or Aquarius is failing. So we need to fix that one, where it is failing and all. So the same thing we are doing with the Pacific Ocean, the Pacific Ocean also doing pretty good. All these, both satellites, models, and all those things. And Indian Ocean also. Indian Ocean, the problem is the North Indian Ocean. So the North Indian Ocean always have problem of the, as it mentioned to you, the radio frequency interference. So that is causing problem. That's why we are not getting 0.8 or 0.9. Can you see here? 0.7 we are getting. So still a lot of points we are missing. And also, of course, I'm showing you here only the best examples, right? So if I take different months, you may not see this good correlations, right? So still we are working, and if you come to the world oceans, still you see, it's not very good in some places, whole world oceans like that. So we need to find out. So this is a boring slide. I want to, don't show this one, but what I want to show is to the R square, doing pretty good. So the Aquarius satellite is doing very good, for this kind of study. Okay, so quickly I will show some slides on the freshwater and saltwater. So this was showing the saltwater, zonal and meridional. So if you take the how much salt is moving, like latitudinally, then you can see here the aqueous average. So you can see the high salt is moving from here to here, right? So like that you can see in the tropical regions, and also you can see in the southern ocean the salt is moving here. But you see the meridionally the salt don't move much because most of the currents are moving east-west, right? So that's why the salt is moves in this direction, or the fresh water moves in this direction rather than moving in the meridional direction like this. So you don't see much difference. The same thing if you take the fresh water also moves in this direction much, you can see the lot of fresh water because it's all due to the ice melt, right? So you can see very clear with this satellite. So this is the new finding we have seen, and which was published in 2011 by my student Ebenezer Nitro. What she showed is in the Indian Ocean, you have the positive transport only in the northern Indian Ocean, but a negative transport in the southern Indian Ocean. What it shows is all the salt in the Arabian Sea water is pushing to the southern, southern Indian Ocean. So we know that there are a lot of salt is here, right? But the salt is moving to southern ocean. So what happens in few years? It will become fresh and fresh, right? So because the salt is moving here, but luckily the Arabian Sea water, the Red Sea waters are still very high saline waters, right? So still the salinity is coming, the salt is coming from the Red Sea, Persian Gulf area. Still the salt is coming, right? So this is the so the Indian Ocean is a net exporter of salt to other oceans or the Southern Ocean. So that is a new finding we have seen. So if you look at the quickly in the Indian Ocean, the North Indian Ocean is completely landlocked, but the Southern Indian Ocean is open to the Southern Ocean, and also the Pacific waters can enter into here, and the Bay of Bengal is less saltier or fresher than the Arabian Sea. So we know that the fresh water from the Bay of Bengal waters comes here, and the saltier waters goes like this one from the model simulations like this one, right? So, but we don't know how much water really moving from here to there or there to here, right? So now from the satellites you can see that how much really water is moving. Can you see the movie shows this is all the low salinity waters or fresh waters, and here we have Ganges coming, fresh water is pumping, and that is coming, and you can see the freshwater movements, and the salt water from the Red Sea is coming here. Can you see here? So you can quantify how much the fresh water or salt water is coming or moving from one basin to other basin by using the satellite data like that. So that is the advantage of this work. I'll show. And also we are using the hybrid coordinate ocean model. So if India and Sri Lanka is there, there is a small strait is here, which is very shallow, 40 to 60 meters deep, but a lot of fresh water moves from here, and also a lot of salt waters migrate from here to Arabian Sea to the Bay of Bengal. So it's very interesting to see here. So this is the satellite data showing. You can see here all the fresh water. In the SMOS, we are not showing here because of the RFI problem, but you can see in the Aquarius, you can see the pretty clear that one. So even though you are seeing from the satellites and models, everything is showing the fresh and salt water, but lot of difference is there still, one PSU to one PSU. So we have to minimize these errors in the next few years. Doing a better algorithms and all those things. This is what I want to show you. How we do the validate, how you can tell the satellite doing good. So when the satellite is going like this one, and it gives the antenna, blue, green, red antenna is like this one. So we take the ships. This is another one, Atlantic also I'm showing. In Atlantic, the problem is the antennas don't fall like in the Indian Ocean. In the Indian Ocean, you are getting all in lined up like this very nicely, right? So here when you do observations, when you take your ship, you need to be very careful. You are on one of these footprints, right? So it's very difficult in Atlantic Ocean than the Indian Ocean. So we take these ships like these ones, the Indian Ocean we have, NIO has this ship. I supposed to go last month, but we canceled the trip because we got this ship. This is very small, which is not enough for study in the monsoon. So because monsoon was very strong, and this ship, even though it is a brand new, it is not staying stable, so it's very difficult to go on this ship for 30 or 60 days cruises. So we are scared to go on this one, so we canceled our cruise on that. So that is about the Indian Ocean. And the Southern Ocean is very important for the ocean circulation. I think I have some more time. Quickly, I will go on the Southern Ocean. So where the Southern Ocean looks like this one, Antarctica is here, and you can see the Indian Ocean waters and the Pacific and Atlantic, all the waters were mixing here, right? So the Atlantic is bringing the saltier waters, and the Pacific is bringing the fresher water, low saline waters, and Indian Oceans are also bringing mixed waters. So this is a very interesting area. But the problem is, when it comes to here, the ice is causing problems. So we are avoiding that problem right now. But it's a very interesting area to study. So even in the Southern Ocean, we are getting a lot of differences. See here, the salinity is a lot of difference between the Argo and HICOM. So we need to find out, what is causing the differences and all those things. So if you take the, again, correlations, so in the Southern Ocean, we are doing pretty good, in the Southern Ocean also, means the satellites are picking up in the fresh and salt waters are very well in the Southern Ocean. So this is the one, it's very interesting. I will show you some of the movies on that. For the Gulf of Mexico, we run the ocean model for the Gulf of Mexico, which is a 125th degree nested Gulf of Mexico model. So we use this one for the hurricane prediction or forecasting. So we use the hurricane winds. So the hurricane winds you can get from the satellites data. So when hurricane is passing, then you can see the hurricane in the winds like this one. So if we put those hurricane winds in our model, then you can see, when the hurricanes are coming, these are what you are seeing. The color is the wind divergent and convergent, and the arrows are wind speed. Then you can see the hurricanes are moving. Can you see here? So in the hurricane season, we run this model from June to November, and we will see how many hurricanes are moving and all those things. So this is another major research in our lab we do. Like last month, we have a hurricane was moving, so we were looking at where it is moving and all. So we are very much interested whether it is coming to the Carolina coast or it's going to the Gulf of Mexico, like those things. And also, we are interested on the Gulf of Mexico because this is the loop current. This is the loop current like this one. It goes to Florida current, and it becomes the Gulf Stream, right? So when it is so you can see here Mississippi. So what you are seeing here is the background is the surface salinity, and you can see the fresh water from the Mississippi River is coming and going into the Gulf of Mexico. You can see the fresh water, right? So all this is the fresh water is coming here. And this is very interesting because a lot of oil industries are there. They want to know how this eddy is, how deep this eddy, and what are these velocities, currents are here, because they do the offshore drilling. And if the offshore drilling they are doing in the eddies, it's very difficult because the currents are strong, right? So they want to see what is the diameter of this eddy and how deep this eddy and how long this eddy stays here, because all these are unstable. These eddies don't stay longer than 2 or 3 months, right? So they have to wait for the offshore drilling and all those things. So a lot of industries are interested in getting this kind of information from us. and also you can see the temperature. So SST is very important for the hurricane prediction, because by May or June, if you look this picture, it will all red, right? Because the sea surface temperatures are very, very hot, and that fuels the hurricane. If you have the hot sea surface temperatures are here, or higher sea surface temperatures, and if the hurricane enters into this one, that fuels the hurricane, and it can become from category 1 to category 2 or 3 or 4, depending upon the how much strength it can gain, due to the like that. So this is, so we do this kind of work too, in the Gulf of Mexico. So this is the one, Michel Garek, one of my PhD students, did this work when Hurricane Katrina was there, and you can see the hurricane winds are very strong, Hurricane Katrina, and it caused the upwelling, very strong upwelling here. So you can do a lot of biophysical studies also, and how much the phytoplankton or zooplankton is coming to the surface and all those things. So this is another thing, salinity. So we are interested on whether the hurricane changes in salinity. So you can see when the hurricane is there, you will see a lot of rain, and the rain in the Mississippi River, a lot of rain is there. So that's why you have the low salinity waters are here. So the low salinity waters can also penetrate into the to the Gulf of Mexico. So you can see all this area is low salinity waters are there, and the low salinity waters are now slowly penetrating into the Gulf of Mexico like this one. So you can study the plumes, river plumes, and all those things, using the this kind of model. And also we want to study how the relation with the this is the loop current, and this is the eddy, and then you can see here this is called sea level. So a lot of sea level changes here, that is causes the storm surge, right? During the Hurricane Katrina, it killed a lot of people due to the storm surge, right? The storm surge also, you can see the storm surge is, sea level is changing here along the coastal regions when the Hurricane Katrina was there. So we did a lot of work on that one. So this is the one when, Deepwater Horizon. Have you heard about that oil spill in the Gulf of Mexico? Everyone might have heard, right? So everyone came to our lab, even the vice president of research. He asked us, can you run the model and tell us how quickly this oil comes to our Carolina coast? Then I told, it never happens, because it never comes, that one, because this Deepwater Horizon, the oil spill was happened in an eddy here, right? The eddy was not touching the loop current any time, right? And if the oil spill entered into the loop current, then it will be matter of 7 to 10 days. You will see here the oil spill should have come to our coast. And if comes here, and once you enter into the Florida current, it goes into the Gulf Stream, and it can go all the way to the Europe. You must have seen there was a paper in Science, one guy published a paper saying that this oil spill can enter into the European waters. Yes, it can enter into the European waters first if it enter into the loop current, right? Now, if you're not entered into the loop current, how do you publish a paper showing that it is coming into the Europe, right? So there is a lot of debate and worry, a lot of people about this one. But a lot of people talk, but not really they do science, right? If you run the model, you know that where it is going really. So in our lab we are quiet because we know that it is not going anywhere. So it went only to the Pensacola and Florida in the coastal regions, because this eddy is mixed with or combined with another eddy, and so that's why we got some of the the oil on the coastal regions in the Florida and the Gulf Coast, but not on the Carolina coast. Right. So that is another study, we did that. So what is in next 5 years, what I want to do, or my group want to do, is we want to do this kind of, global conveyor belt. So, So the global conveyor belt is very important, to circulate the water from one area to another area like this one. So this is the very schematic. Last 20, 30 years ago, people have done this one. But recently, the IPCC, which is called Intergovernmental Panel on Climate Change, they got the Nobel Prize, right? You know that, right? The IPCC and Al Gore got the Nobel Prize for doing this kind of study. So what they showed was, the conveyor belt should not be like this one and should be like this one. So they added some more, areas like this one. So the warm currents are moving. The red ones are warm currents are moving like this one, and the blue ones are deep currents are moving like this one. So the water is moving like that. So now if you know the salinity and temperature, you know the density, and you can do this kind of thing. This is all schematic. If you really went on the ocean, you don't see this kind of belt, right? So what you're saying is these waters might be going up to here. And why can't these waters can go all the way to Arabian Sea or the Bay of Bengal? Why can't you go upper, right? So you need to do more research on that and how really these waters are moving. In the past, the people, we used to think that this warm current used to come straight here. Now we are saying this warm current is connected with the loop current also, right? So a lot of changes are there in the global ocean circulation, so it's very important to know all these things. Okay, I'll stop here. Okay, great. So, any questions? I will be here. So, yes, sir.
So the radio frequency interference is seen in the North Indian Ocean.
Mm-hmm.
How homogeneous is that? Or is it's really super variable such that you couldn't put out either probes or floats to take data at the exact same time and try to correct for that?
Right. So that's what we are doing right now. So, but the problem is still the frequency. It's not fixed frequency, right? So different cell phone companies are using the different frequencies, but all are causing the problem to the sensor. So we can fix that one by using the different algorithms or corrections. So we can do that, but it takes some time. So if you look at our SMOS data, last year data and this year data, it is much improved. But still, I'm not confident that we are minimized it to 100%. So, yeah. Yes.
I have a question. You show that the salinity is kind of related to the temperature,
Mm-hmm.
and that temperature is only a parameter that affects the salinity, or it has some other parameter.
No, the salinity is not directly connected with the temperature, but the salinity and temperature can change the density. So the density is function of temperature, salinity, and the depth if you're going to deeper layers. But in the surface layers, I would say the density is a function of only temperature and salinity. When the salinity changes, temperature may not change, right? Or temperature change, salinity may not change, but the density can change. So then the circulation of the waters are changing, either temperature changes or salinity changes, the circulation pattern changes. Yeah. So to understand the hydrological cycle, you need to have both parameters. You need to understand very accurately. We can measure the temperature up to 0.1 or less than 0.1 from satellites. Because the satellites are there to measure the sea surface temperature from 1975. So we have like 40 years of data, and we have knowledge how to fix that, to get the higher accuracy in temperatures. But the salinity just started, so we are looking at different algorithms and all, how we can get to higher accuracy. I would say even we need to go below 0.1, to get more accurate salinity at some time. Yeah. Yes.
You mentioned the use of the Argo buoys for this, and I think we talked earlier
Right.
that one problem with the Argo buoy is that it doesn't go all the way to the surface.
Right. It's a
Have
5
you taken a
meters.
look at any of the marine mammal data that's coming out now?
Yeah. So.
Taking them out of
Right. In the MBRI, Monterey Bay, California, we have some whales and dolphins. They connected some sensors data. The problem is they don't go all the way to the surface. They go to deeper layers and come back. So you get like a profile data, not at the surface like that.
Right. But
So
you do get when they surface debris.
yeah.
Surface
Salinity we get, but that is very random, and we don't have a lot of points on that. Yeah. So because when I was at Florida State, we used to do the similar kind on the atmosphere for the birds. So we used to put a sensor on the birds and to get the upper atmosphere, like temperature and pressure and the winds and all those things. The same technology we can do here too, but very random data you get from those.
So a big problem is trying to get temperature sonograph data from ships, I think.
Right. Yeah.
Continuous profile.
Right. But the problem is we have very, voluntary ships are very few. Not all the ships have the thermosolenographs. Yeah. So that's another problem. Yes.
You mentioned that you get your daily satellite data, right? And you run this model
Daily.
How do you use the satellite data? Is it like the boundary conditions or?
No. The satellite data we don't simulate or anything in the model. We use only for the comparison purpose, validate. Yeah, so only for validation. But once the satellite data, we are confident that it is coming very good, then we can use to assimilate and we can use in the forecast model. So that is the long-term goal to use for the forecasting, the temperature and salinity. But it may take for a while. Yeah.
Is there some of that work that's being done in operational oceanography?
Right, yeah. The Navy is using the same model for their nowcast and forecast. The same model they are using for the nowcast.
So they nudge the salinity data with
No, not yet.
satellite.
Not the salinity data they are not using yet.
So this year, some news stations were mentioning that Japan tsunami waves causing even more problems than they usually thought. Do you know about any predictions of the diffusion of these?
Right. So actually, the Navy is using the same model to track the debris are coming from the tsunami. So Navy is doing that. Actually, one of my students, Dara Karen, she's now a federal employee in that Navy at the Stennis Space Center in Mississippi. One of her work is to use this model to see the debris, and suppose if something happened, shipwreck or something happens, she gets this data and she can monitor where the currents are there, and she gives that kind of information. So Navy is doing that. Yeah. So that is another advantage of my students. Once finish my lab, they get the jobs either in NASA or this Navy or like NOAA and all these kinds of things, because they see what kind of work we are doing, and also immediately they grab them from our lab immediately. So all my 3 students, they got the federal jobs. They are earning more than myself. So yeah. And one of my students, like Michelle, she's working at JPL NASA. She has 10 people are working for her. And she just graduated in 2009. And she always tells me, I will hire you. Yeah, she just graduated 4 years ago, and she tells me, I will pay more than what the university is paying for you. Yeah, but
I have 2 questions probably related. One is for the Antarctic. I see you have a mask.
Right.
You use the satellite don't go to inside the mask?
No, no, it goes all the way. In Antarctica, you have very small region. You miss, the only the ice part you miss from the satellite.
So you have once you have the ice, you don't get it.
No, yeah.
But once the ice melts, you get it.
Right, you can get the data. But the SMOS goes all the way to 90 north, 90 south, pole to pole it goes. So we can get from SMOS the data, but the problem is SMOS, how good it is, we don't know on the ice still. So.
You didn't mention anything about the Arctic Ocean. I don't know if able to look at the satellite data for the Arctic Ocean.
Mm-hmm. Yeah. So we can, again, in our study, because we are interested on the global, so we are removing the polar regions, so we are not going all the way there. So because sometimes it is contaminated for our studies. So because right now what we are doing is we are quantifying really how much is becoming saltier. Is it 10 PSU is becoming or 20 PSU? So we want to quantify. So that's why we are removing the polar regions at this point. But we have the data in our disks, all the data all the way. So, yeah. Every day my students, they process and they keep all the data, so.
How long we doing the kind of validation in the Arctic Ocean?
Right, there are, people are doing. There are 15 scientists, we are on the science team. There are some people are working on the Arctic and, so, yeah, thank you. Thank you so much for coming, yeah.
So you do have a kind of
Yes, I do, but then you have a procedure, right?
Okay.
Not like what's part of the Okay. So they'll be joining us, so we can just go to one of the Mexican restaurant here.
Oh, okay. Yeah, sure. Yeah, that's good.
So you guys are come here and just so these are my students who just
Okay.
you can meet them. He's Chad.
Oh, okay. Hi, good to see you. I'm Subra. It's good to see you.
So after the lunch, if we have some time, we can just go to
We ought to teach on one.
what time are your labs?
We're going to do from 1 to
1 to 4. We're going to be going off camera.